Hello, my name's Anthony Cook and I'll be presenting our report for assignment 2. And before I begin, I would just like to thank my co-authors for all of their contributions. The presentation today is going to cover a brief overview of the problem space. I'll be covering our optimization parameters and the strategy that we chose. I'll look at how we generated our buy and sell flags for the trading bot, and then I'll review the process that's in play for our evolutionary strategy. Finally, I'll wrap up with our model performance, the evaluation and results, as well as the conclusions and recommendations going forwards. The problem space is simply wrapped up in terms of the goal of our trading bot is to optimize the trading events to maximize its final portfolio value. This is with an input and other constraints such as the commission value, and this is done through the use of the evolutionary algorithm to optimize those buy and sell flags. The data that we're using is sourced from the online Kraken database and includes the OHLC data table as well as date data for those records. The optimization parameters themselves are the inputs that we're going to be using to generate those buy and sell events, which we'll be referring to as flags from here on out. So let's have a look at the parameters and strategy. Before I get into the details, I'd like to introduce the EMA, which is the exponential moving average metric. This is a very commonly used metric in technical analysis for traded stock, and it's quite useful for traded stock in that rather than a simple moving average that you would normally see, recent prices in the moving average equation have a greater weight than others in the population. And this is particularly useful so that the EMA is more sensitive to events and changes in the market as they are occurring. It's very useful because we can set any period for this exponential moving average, and in particular, the wider window that we choose for the EMA, we have a less responsive EMA, and if we have a tighter window, so smaller values, then we end up with a more responsive EMA. When we use the EMA in our strategy, we are using the triple exponential moving average strategy. This is a strategy that uses 3 EMAs in conjunction with each other. So we have a short, medium, and long EMA, which follows the constraint where the short EMA is a smaller window size than the medium EMA, and obviously the medium EMA is a smaller window than the long EMA. This strategy has a few benefits. Some of them are that it allows us to be more responsive to price changes. With the multiple EMAs, we can reduce the lag time and in particular reduce false signals that we might get with just one EMA. It's quite a versatile strategy, and it has a key appropriateness for the problem space itself in that we are able to use a genetic algorithm to solve the multiple optimization problem, the multiple optimizations being each of these EMA window sizes. To generate the buy and sell triggers from the triple EMA, we first can consider this toy data set here, and the long-term EMA will be a smoothed representation of this data set. The medium-term EMA will be a less smoothed representation, and the short-term EMA will be the most sensitive to the changes in the data type. From this data, we can use our rules to then look at when the short-term EMA is either above both the medium and long-term, or below the medium and long term. And we can flag, or we can illustrate the flags of the buy and sell as such. So here we can see in the first instance we have a buy flag where the short term crosses over the long term. And again we can see the benefit of having the medium term in the second flag, the sell flag, where it dips below the medium. And it does so slightly later than it dips below the long term. And it's this interplay that we're really going to be relying on to help optimize the algorithm itself to be sensitive to these changes and fluctuations in the prices. The evaluation of those parameters is fairly straightforward. We take as input those dated buy and sell triggers. We apply them to a historical data timeline as a simulation. So this would be the OHCL data. We then track the portfolio value, incurring a 2% handling fee at each transaction. So that's a 2% loss at either a buy or a sell. And then we output the final portfolio value that is generated. And this becomes the fitness function that we are trying to optimize through our evolutionary strategy. To review the evolutionary strategy that we chose, so we begin with an initial population, which is a random initialization of the 3 EMA ranges. And these ranges could be not adhering to the restraints which we referred to earlier, such as the final EMA combination in this list, where we have the medium EMA being less than the small EMA. And we wanted to do this because we didn't want to restrain the EMAs of the small, medium, and large to any one single bin width, so that the algorithm could then explore the entire space. In the event that this occurs, we evaluate that to a -infinity so that it doesn't get included in the process. And for all other populations, all other solutions, we evaluate the performance of that on the portfolio as normal. So from the initializations, we get our evaluations. These evaluations then go through a tournament selection process. So this is where we begin generating a mating pool. So we randomly pick 2 parents from each of these populations, or rather 2 contenders, and simply the highest one is the winner of the tournament and gets added to the mating pool. We repeat this process until the mating pool is the same size as the current population. And in this way, we are able to remove some of the weaker players and duplicate some of the stronger parents, so that the mating pool has stronger genes overall. We can see that we've dropped out some of the lower ones in this case. However, we do have the instance where the very small ones can still be added if they're paired with even smaller ones. The mating process itself, so going back to those EMA values from that mating pool, is simply choosing pairs from that mating pool as parents. So each parent can only be chosen for one generation of offspring. So in this case, we take those 2 parents and we use 2 methods for creating the children. The first is the SBX, which is simulated binary crossover, followed by a polynomial mutation. And these techniques are shown in the Algorithms for Optimization book, which is listed in the references there. Through this process, every pair of parents can generate 2 children, which will then enter the pool for the next generation. We simply repeat this process for as many generations as we need and keep track of the highest performer. So the final parameters that we need for this process is to pick the population size, so the number of individuals within each generation, and the number of generations or iterations which we will be going through throughout this evolutionary practice. As I mentioned, the optimum solution is the highest performing parameters throughout this entire process. The last thing that we need is the data. So we have chosen to use 2 years worth of data from January 1st, 2021, which carries through to January 1st, 2023. The parameters are optimized on the first 12 months, and the validations of those parameters is given on the second 12 months. Moving on to model performance. So one thing in particular which we noted was that we converged to an optimum solution extremely quickly. Sometimes we found an optimum solution in the first generation, and other times we were there within 5 generations as shown here. This is something that we explored a little bit further, but ultimately we feel that it is contributing to an overfitting of the solution space. Perhaps that is a little bit too simple for the techniques which we have generated. When we look at the evaluation of these techniques, we see this in greater detail, where the training results, which is given by those 3 SMEs, or EMAs rather, gives us a profit of $151, or a final portfolio value, which is roughly 50% return on our investment. In contrast, the evaluation result, which is on the second 12 months, only returns $67, which is a decrease of around 30% of our initial investment. So this is leading directly into our observations, which is first and foremost that we are likely overfitting to our training data set. And secondly, that the validation data set is not generating a profit, and potentially because the second validation data set is not optimal for making a profit. So the timeline itself may be quite challenging in its ebb and flow of those values, which means that perhaps it is not able to make a profit in that time period anyway. So some of the recommendations from us which come out of this is that we would look into doing further study, which is to adjust the training process to reduce the likelihood of overfitting. There are several ways we could explore this. One would be to implement some kind of variable time periods rather than the static 12 months that we fit to. We could test with different lengths of time periods as well as multiple time periods. We could also look at reviewing our evolutionary method. We are using a TEMA strategy, but we could look at some of the other metrics, the other technical analysis metrics which are commonly used, and find other ways to introduce those as additional parameters for optimization. And this may make our technique a little bit more robust against unseen data. I'd like to thank you for listening and encourage you to read our report for further information, and our references are as shown. Thank you very much.